for the kind invitation for me to deliver the Icon X talk for this Friday. A very warm good evening and good morning and good afternoon, depending on where you are, to everyone online. Professor John just gave a very nice introduction on my background. So I'm Dan Lee from Department of Physics, City University of Hong Kong. So in today's talk, I would like to focus on one particular material system, which we call it nickel oxide or nickelates. So this family of materials recently emerged as a new family of high temperature superconductors. So throughout this talk, I would like to walk you through some history of superconductors by introducing the beautiful properties of these materials, and also to ask a very simple question, why we want high temperature superconductors. And hopefully after that, I will lay out the foundation for the discussion on this new family of high temperature superconductors, Nickelates, and discuss a few aspects on this fast developing topic. Okay, without further ado, let me begin with some background knowledge on superconductivity. So superconductivity, I just copied this definition from Department of Energy, United States. Superconductivity is the property of certain materials to conduct a direct current, electricity without energy loss when they are cooled below a certain temperature. Right? So from this definition, one can already see that superconductors or superconducting materials, they are a group of materials which do not have resistance at all below a certain temperature. At the same time, we also can see that usually superconductors, they become superconducting at extremely low temperatures. Okay. At the same time, they also expel magnetic fields when they are in this fully superconducting state. So this is why in scientific gatherings or activities or secondary school students' activities, people like to show this kind of demo experiments where a superconductor, when cooled below a certain temperature, they can flow above a magnet. And people believe that the superconductivity is fascinating and can be characterized as a mysterious state of a matter that would find their applications in many, many occasions, including medical diagnostics and also fundamental research. So I will try to explain this in more details later by giving a few examples. So if you think about it, superconductivity as a phenomenon is quite mind-boggling because it possesses zero resistance and also expels magnetic field. To put it in more understandable context, I like to show this screenshot of a movie. Some of the audience probably already recognize what movie that this is. So this is from Avatar, where all these floating mountains or islands in the sky on this planet, right? And in order to understand why these mountains are floating, we need to seek for knowledge on superconductivity. This is what I just told you. And the reason that these mountains are floating is precisely because that the materials made of these mountains, they are called, in the movie, called unobtainium, right? Probably means that on our Mother Earth, there's no such materials yet, right? So this is why it's called unobtainium. And this is a cause of a source of a conflict, at least in the movie, right? People are fighting for these resources, and simply because they are, room temperature superconductors, as they expel magnetic fields generated by the poles of the planet, right? Pandora. Of course, you can see here now already the difference between the situation I just described in the previous slide and the situation here in the movie, right? Unfortunately, or maybe fortunately, so far on Earth, we can only have superconductors at extremely low temperatures, and on Pandora, on the other hand, it seems that they have room temperature superconductors. As a matter of fact, you can buy, this kind of toy on Amazon very easily to have this a floating magnet. Of course, this is due to something else instead of a room temperature superconductivity. Okay, to put a superconductivity in a more physics language, this is to say that if you measure a resistance or resistivity of a superconductor, when you cool down in temperature, the resistance drops to zero, right? Marked by these abrupt transition. While for normal metals, you will see a continuous change in resistance. Okay, so I guess a lot of people in this audience know the discovery of superconductivity. So this was discovered in 1911, more than 100 years ago, by a Dutch physicist, Caroline Ooms, who was a pioneer in liquefying different gases, including helium, and precisely because the liquefaction of the helium, he was able to see phenomena, including superconductivity, way below normal temperatures. Okay, so when he wrote down in his notebook, he gave a name to this phenomenon, superconductivity, of course, not in English. And this was the beginning of the study of superconductivity and superconducting materials. Of course, the first material he discovered as a superconductor is extremely low temperature superconductors, which is mercury. And after that, many superconductors were discovered alongside with some interesting properties. I call it beauty of a superconductivity, including a Meissner effect, which was discovered in 1933, already more than 20 years after the discovery of superconductivity. So Meissner effect tells you that when you apply magnetic field to superconductors, these magnetic fields are going to stay outside of the materials completely. Okay, for at least for certain type of superconductors. So this complete expulsion of magnetic field marks another intriguing property and a phenomenon that these superconductors possess. After that, many famous physicists, material scientists, jumped into the field trying to, number one, understand the mechanism of superconductivity, and number two, develop new materials and trying to discover more and more superconductors. And these big giant physicists all contributed to the understanding of the superconductivity in one way or another, and establishing superconductivity as one of the most celebrated and phenomenal macroscopic quantum phenomena. And all these gentlemen won a Nobel Prize because of this. Of course, and there was not only a success, but also failures. I like to talk about this, particularly to intrigue young people working on material science and physics, just to tell everyone that even among the most brilliant minds of humankind, including Einstein, Heisenberg, and Feynman, all these are big names, they try in different ways to understand why we can have superconductivity, but they all failed. So they came with theories eventually could not fully understand superconductivity, although they have achieved, various achievements in different fields. I think the most successful story in terms of understanding superconductivity itself came with so-called Bardeen-Cooper-Schrieffer uh, theory or BCF theory, where they introduced a key concept of so-called electron boson coupling, as we now refer to it, where they argue that in the material, the lattices can do something very unique, right? Through their vibrations, they can bound the electrons and form the electron pairs. And these electron pairs are so-called Cooper pairs. Once formed, they will condensate into the superconducting state. So BCF theory successfully explained why we can have macroscopic zero resistance or superconducting state. And because of this, after 15 years of their series of papers, they were awarded Nobel Prize. Okay, and this is the first and so far the most successful model or theory in explaining why we can have a superconductivity. And of course, this theory also has limitations. Particularly, this theory is valid and is very successful in explaining the elemental superconductors. And these elemental superconductors are the majority of the superconductors which were discovered at early stage, right? People just go through the elemental table and try to measure each of the element down to low temperatures to see whether the ground state of the system is superconducting or not. Okay, and including some of them, although not superconducting under normal pressure or ambient pressure, but it becomes superconducting under high pressure. Okay, overall, all these elemental superconductors, their superconducting properties can be well described and captured by what we just said, BCS theory. Okay, so far so good, right? So BCS theory works very well, and although after almost 50 years, 40 years after the discovery of superconductivity, it can explain the phenomena that we see in these particular group of materials. And people, including Macmillan, and try to develop all sorts of theories based on this BCF theory and try to calculate how far we can go. Meaning that from theoretical point of view, different models can give predictions on the transition temperatures or below which temperature, what temperature the materials would become superconducting. Okay, so this Macmillan limit proposed by Macmillan, when unfortunately passed away at the age of 48, suggests that in these normal superconductors, we have a fundamental limit using the electron photon coupling to explain superconductivity, which is at 40 Kelvin, roughly. Okay, so this over the years started become a benchmark for discovering new superconductors, right? If a new superconductor with transition temperature above this temperature, 40 Kelvin, we can roughly regard it as a potential high temperature superconductor. Okay, so this marks, I would say, the beginning of the story of high temperature superconductivity, and I would like to use it as a teaser for introducing why we want to move to high temperature superconductors. Okay, so even before that, many physicists, material physicists, and material scientists worked very hard in finding superconductors with higher transition temperatures, including this material physicist Matthias, who throughout his life have discovered many, many superconductors. So he gave this very famous Matthias rules from an experimentalist point of view. Okay, so he said, if you want to find good superconductors or with higher temperatures, he argued that high symmetry is good. Possibly cubic symmetry in terms of lattice symmetry is the best. And high density of electronic states is good. So for physicists, we know density of states, if it is high, it's good for superconductivity. And stay away from oxygen, stay away from magnetism, because magnetism, in principle, can kill superconductivity. And we want to stay away from insulators, right? Because we are finding materials which conduct electricity almost or at a perfect level, right? So we want to stay away from insulator. And last but not least is stay away from theorists, okay? Although all these rules listed above, except the last one, turned out to be not precise, not true, as I will introduce the family of high temperature superconductors. They all disobey all these rules, but the last one in the community, was a quite interesting and highly mentioned joke for people working on high temperature superconductors. Okay, people like to tease about this, meaning that to precisely predict particular TC of a superconductors is always very difficult. Okay, so let's move on to this fundamental question about why we need high temperature superconductors. Okay, so from a purely practical point of view, I would like to list a few examples, particular application examples, to motivate the audience why we want to develop, why we want to spend energy and spend resources and money onto this fundamental research field. Because this is precisely because understanding of superconductors, especially high temperature superconductors, has profound impact on transforming our everyday life. Examples span from electric power transmission. This is something everybody can easily understand. If you have zero resistance in the material, you can, conduct electricity without any energy loss, right? That would be perfect if we can send electricity and energy, to a distant place without the worry of dissipation. The next example is that everyday in everyday life, if you go to hospital, if you want to do any medical imaging or diagnostics, we need to use MRI machines, right? One of the factors that limits MRI machines' resolution is the magnetic field and how stable the magnetic field is. So if you have a superconducting coil and you can send a constant current along the coil, you will be able to generate a very stable and high magnetic field, which can be beneficial to these MRI machines. Okay, so maglev trains, if you have a superconducting material, since expel the magnetic field completely, you can imagine a situation that superconductors, trains or trails made of superconductors would perfectly lift the trains so that you have zero resistance frictions when you have trains running, right? Also, for scientific research, similar to the MRI machines, if you have a superconducting materials, we can generate large magnetic field that can be utilized by scientists. For instance, this is a picture taken underground in CERN, right, where you can conduct very large scale fundamental research on particles, for instance. Not only we can utilize superconductivity and superconducting materials for large scale applications, but we can also look at devices, including superconducting quantum computers and superconducting quantum interference devices. And nowadays, all these devices, most of the devices utilize superconductivity, but at extremely low temperature. Again, if we imagine we can operate these devices at much elevated temperature, we would be entering a completely new era, right, with quantum computers and quantum devices in play. Okay, so all these are quite phenomenal and everyday applications of superconductors. We want to make high temperature superconductors or even room temperature superconductors precisely for these applications. Okay, so where to begin with high temperature superconductivity? I think the story, it's fair to say that this story began in 1986. So in 1986, these two scientists at IBM Zurich lab, they synthesized a copper oxide material, which turned out to be superconducting at a relatively high temperature. Okay, and because of the fact that this discovery was so mind-boggling, and after more than 1 year, roughly 18 months, these two gentlemen were awarded a Nobel Prize for their discovery of a high-temperature superconductivity in a copper oxide or a cuprate. Okay, so that was really the beginning of a golden era of study of high-temperature superconductors, particularly on cuprates, which I will come back later. Okay, so cuprate so far holds the highest record in terms of TC, transition temperature, and it proves again that nothing is impossible. It is precisely when people find it's very difficult to raise, the transition temperature of the new superconductors. This discovery came up. And Chinese scientists had made a seminal contribution to this field by discovering so-called YBCO nowadays. And it's very easy to synthesize these YBCO materials. And these materials possess transition temperature that is above a liquid nitrogen temperature. Okay, so this is, I would say, a key driver for this Nobel Prize. So roughly after more than 20 years, Professor Hideo Hosono in Japan discovered another family of a compound, which turned out to be superconducting at a relatively high temperature. And these compounds, because they contain iron in their chemical formula, so these compounds mark the beginning of the Iron Age of superconductivity or high temperature superconductivity. And again, Chinese physicists and material scientists had made phenomenal contribution to this field. I just would like you to look at this graph. If you look at the timeline or stamps for discovering new materials, iron-based superconductors, you can see that the competition back then was very severe, right? So these discoveries were made in the measure of days rather than months, right? Many of these compounds were discovered by Chinese scientists. So in 2019, when I was doing my postdoc at Stanford, working with Professor Harold Huang, we successfully synthesized a nickel oxide compound, which conduct superconductivity. Okay, back then the temperature was not very high, was roughly at 15 Kelvin, so 15 degrees above absolute zero temperature. But that was successful finding after more than 30 years of a quest for superconductivity in nickel oxide or nickelates. Okay. So the materials that were discovered, which were superconducting, was the neodymium strontium nickel oxide, one type of the nickelate compound. And this discovery triggered a plethora of research activities. And up to now, we're in the exciting world of superconducting nickelates. Particularly, I would like to talk about, in today's talk, is just one family of nickelate compounds, which are the infinilar nickelates. Okay, so just some interesting story to share before I jump onto the really scientific part. So one day before I found this a superconductivity in the nickelate compound, I was walking on the campus, Stanford campus, and I suddenly saw this on the road every day that I walk to the lab. You see this branches. They look pretty much like a superconducting transition, right? So the resistance goes down and goes to absolute zero. Okay, so I posted one WeChat moment. Have you ever seen a superconducting transition in your life? Only through the eyes of a true scientist may a nobleman see the manifestation of a God's revealing. So I was working already on the Nicolate project at the time, and I was thinking this could be a good sign, finding superconductivity. And it turned out to be true. On October 25th, 2018, so 2 a.m. in the morning, so very late night, on our measurement system, I start to see below 10 Kelvin, the sample that I measure at the time start to show a resistant drop. Okay. On this sample, it was showing a resistant drop, but the resistance was far from being zero. Okay. So this is a picture that I took during that night showing the raw data of a sample. Okay. So this was a quite, of course, a quite exciting moment. And only after a week, we start to see zero resistance in these samples. However, it took us almost 8 months to reproduce the results and the samples in a very robust way. Okay, so it took a very long and painful 8 months. So in 2019, June 29th, we submitted the paper to Nature, and only took about a week to get in principle accepted by Nature. And it's very interesting, the materials of supplier start to follow us. So they start to make a target and materials precisely following the formula that we posted in this first Nature paper. Okay. Anyway, that was some stories behind the discovery. And because of the discovery, I was very honored to be listed on the MIT Technology Review Innovators under 35. Okay, so the materials that I just mentioned was one type of nickelates, which possess infinilar structure. So 2 years ago in 2023, a group in San Yat-sen University led by Professor Wang Meng, they discovered that in another compound, a 327 compound, because of the chemical formula, if you apply pressure on these compound, you can see superconductivity with a very high transition temperature above liquid nitrogen. So this marks the second example of finding superconductivity above liquid nitrogen temperature in a material system, right? Of course, after this discovery, people jumped onto this field with a very general goal of finding more Nicolate superconductors with higher transition temperatures, hopefully above liquid nitrogen temperature. Okay. Another example, which were later discovered by a group led by Professor Zhao Jun in Fudan University, show that a 4310 compound, Nicolate compound, also shows superconductivity under high pressure. Okay. So since I'm from a thin film world, these discoveries have enlightened the pathway forward for me, at least, that the thin film would be a natural way to go because we can use the thin film heterostructures by growing these materials on a single crystal substrate to introduce the needed pressure and hopefully to stabilize these superconducting state at ambient condition and ambient pressure. Okay. So actually, our peers, colleagues in the field had done quite remarkable pioneer work by growing these series of thin films, including the 327 and 4310 phases. Okay, so the message here is that indeed we can grow these thin films. Okay, but back then, superconductivity in these thin films were not seen. It's only until last year, end of the last year, 2024, two groups, including my former postdoc groups at Stanford, and also a group led by Professor Qi Guanxue and Zhuoyu Chen in South Tech, they discovered that by growing these 327 phases and trying to introduce a oxygen composition mechanism, the material can become superconducting at ambient pressure with a transition temperature as high as 48 Kelvin. So this is already remarkably higher than, let's say, the first superconducting Nicolate that discovered in 2019, which back then was having TEC of 19 Kelvin, 15 Kelvin. Okay, so these are very recent examples on the very fast developing field of the Nicolate superconductivity. Okay, people are trying very hard day and night to grow different materials and hopefully to raise the transition temperature as close as possible to liquid nitrogen temperature or even above. Okay, so with all these background information, let me jump onto my talk today. So I would like to talk about one particular type of Nickelates, which I already mentioned, inflator Nickelates. And by showing maybe two materials examples or materials efforts representing our recent work in finding higher TC in Nicolate compounds. Okay, so let me begin with a little bit the introduction of the inflator Nickelates. So you have already heard from me this story about cuprates, right? So in 1986, these two gentlemen discovered superconductivity in copper oxide compound, and the continuous study and investigation of this system has forged a very important research field in modern condensed matter physics research, marked by this very complex superconducting phase diagram, where you can find all sorts of intertwined phases and very rich physics that have enlightened and motivated other research in condensed matter physics. Okay, so shortly after cuprates were discovered, actually, even before cuprates were discovered, people were wondering whether Nickelates can become superconducting. One particular compound which raised people's eyeballs on this was the so-called inflator Nicolate system. And this is because these inflator Nicolate systems, they possess similar lattice structure to a superconducting inferior cuprate system, at the same time also showing a very similar electronic structure to begin with. Okay, so all these features were captured by early theoretical works represented by these two papers. In these papers, these people suggest that the inferior Nicolate had a very similar electronic structure to cuprates, marked by these hole bands, at the same time showing some electronic pockets in their band structure. Okay, so these discussions, proposals were finally confirmed by recent angle-resolved photoemission spectroscopy experiments, like by two different groups from Fudan University and Nanjing University. Independently, they found these hole-like bands and electron pockets. Okay, so this further engages this important question about the similarities and distinctions between the cuprate system and Nicolate systems in a much broader context, in the sense that if we could answer these questions or figure out what is going on within these two systems, we might be able to understand or solve these puzzle of high temperature superconductivity. Okay, in terms of the material synthesis, we utilize a very special techniques, so-called oxy-deintercalation process, to synthesize these inferior Nickelates. And by using chemical doping to introduce extra charges, we can turn these inferior Nicolate material into a superconductor. Okay, of course, these materials are grown as a thin film on a single crystal substrate. And so far, superconductivity was only observed in these thin film materials, not in bulk for this particular system. And the chemistry behind this material synthesis was, we call it Junga chemistry. So this is to say that these inferior structures were obtained by using a combination of material growth and the post-growth processing by removing the oxygen blocks from the materials in a controlled manner. Okay, so this is just like playing Jenga tower games, right? You want to remove these oxygens without affecting the whole structure of the Jenga tower. So this is a video that we made back then, showing myself playing a Jenga tower game. Okay, let me skip it. So after we found superconductivity and reported in this first paper, many groups have reproduced these results, and up to now, we have already established it as a community phase diagram very similar to the phase diagram of cuprate systems, which consists of all different interesting aspects and properties, phases in these material system, okay, marked by many phenomena such as linear T resistivity, and also sign change or crossover in terms of the Fermi surface or Hall coefficient. So as a material physicist, what I would like to focus on is the strategies on how to increase TC. Okay, so this important paper published a few years ago by Professor Jingguang Cheng's group at the Institute of Physics at Chinese Academy of Sciences has shown that if you put a bit of pressure on the inferior Nicolate system, it seems that the TC can be further enhanced without signature of any saturation. Right? Given the still relatively low pressure applied to the system, this is a very big encouragement for people working on this field to effectively increase TC. Okay, so one way to go, if you think about high pressure experiments, one way to go would be to further tune the lattice constant, hopefully towards a smaller lattice constant. So there might be a hope that we can introduce higher TC in the system. Okay, so that brings me to the key strategies in terms of materials growth. Number one is that we always want to grow higher quality materials. And number two is that perhaps we can tune the lattice in a controlled way or smart way in the inferior phases, hoping to get higher TC. Okay. So in today's talk, I would like to just focus on the second strategy by introducing a little bit what we did in terms of going to a smaller lattice material. Okay. So these efforts composes two separate works. The first one is a synthesis of new samarium nickelate phase with oxygen deintercalation. So this was to go to a smaller lattice system by introducing a smaller ion, samarium ions, into the system. But at the beginning, we failed to synthesize inferior phases, but rather we stopped at a new phases with removing the oxygen. Okay, and the second part would be more recent work that we have posted on arXiv, talking about enhanced superconducting. We do see a very clear trend of higher TC if we move to a smaller lattice constant. Okay. So for the first part, although I'm not going to talk about this in more detail, I just want to bring in this interesting question, at least to me, about zero doping superconductivity. Okay, so as I mentioned, chemical doping is needed to introducing extra charges and superconductivity, right? Recently, people have found that even without chemical doping, let's say without introducing extra chemical doping into the inferior system, it seems that there's a superconductivity existing in these non-doped samples. Okay, so this is discovered or found across different material systems, moving from lanthanum all the way to praseodymium and neodymium. Okay, so this seems to be a very universal behavior or trend, this material system. Okay. Okay. So for these smaller lattice constant efforts, at the beginning, we would like to see whether we could stabilize the inferior phase in the pure samarium nickelate compounds grown on neodymium agate substrate. So you can see from this cross-sectional scanning transmission microscopy, electron microscopy, you can see this materials grows very beautifully on the substrate. Right? You barely find defects in the thin films. Right? And this is also marked in the X-ray diffraction scans or investigations. So we started this from this very high quality thin films. And what we found that is we could not introduce or bring the material into the inferior phase. So instead, we can create some oxygen vacancies, and these oxygen vacancies are highly ordered. Perhaps it's very difficult to see from these very small view graphs, but from these high resolution images, probably you can see that these are the places where the oxygen vacancies reside. You see these oxygen vacancies would expand the lattice, right? Pushing away these atoms, so you can have these very unique periodic structures in these materials. So in collaboration with French group led by Alexandre Glauter, we utilize very advanced 4D STM techniques to visualize the structure and analyze in collaboration. Oh, sorry, in collaboration with the theorists, we analyze the structure of these materials by combining the STM images and DFT calculations. We found out that these materials consist of nickel sitting in different lattice environment. Okay, so within this single materials, we see that nickel can be in a square planar configuration, as well as pyramidal, as well as octahedral lattice configurations or lattice environment. Okay, so we believe this new phase could be a very interesting example system where you can study the nickel coordination as well as the electronic structures and behaviors within a single materials system. Okay. So this is just a summary on what I just told you, that we want to move from the left to the right. We want to move from a precursor phase by using this oxygen deintercalation process to synthesize the inflator phase. However, for this example, we could not achieve it. So we could only stabilize the material in somewhere in between, right? Finding a new chemical formula associated with this new phase. So the reason for that actually is because that the materials, once you improve the material quality or crystallinity, it becomes very difficult to remove oxygen from these materials. Okay. Don't forget that the only way so far to synthesize these material is that we need to remove these oxygen blocks from the materials. Okay. So once oxygen becomes difficult to remove, or at least you need a higher energy provided to the system to remove these oxygens, so the material would become more unstable. So right, so it becomes difficult to achieve this inflator phase. Okay, and so this is why we need a bit of external synthetic method, such as introducing additional ions or dopants into the system in order to utilize the materials modification to achieve this inflator nickelate phase. Okay. So some early examples that are beneficial to our research include research done by Charles Zahn's group at Yale University, where they utilize europium as a dopant into the inflator system, where they could find a very nice superconducting dome, showing introducing europium dopant could lead to superconductivity, as well as more recent examples. So the work done by Ariando's group at National University of Singapore, where they synthesized this very complicated A-side compound, inflator nickelate compound, so samarium europium calcium strontium compound, in which they found a very high transition temperature, almost 40 Kelvin in the thin films. Okay, so this really raised our hope in further improving the transition temperature in these inflator nickelate system. Okay, so we did a very similar things by growing the doped samarium nickelate thin films on a different substrate, so on a more complicated substrate in terms of chemical formula, but in terms of the lattice, it's simpler than the substrate that Ariando's group used. Okay, so from the XRD and resistivity measurements, we could easily identify a very high quality phase marked by all these high crystallinity shown in the XRD, as well as fully metallic behavior down to lowest temperature in our samples. Okay, so after the intercalation process, we could successfully achieve the inflator phase marked by these XRD peaks. And in these samples, superconductivity was robustly shown, okay, with the highest TC around 32 to 33 Kelvin. So collaborating with Professor Peng Gao's group at the Peking University, we were able to look at the crystallinity and crystal structure under the electron microscopes. So if you try to find very hard under the microscope, you do see occasional extended defects marked by these bugs. But in majority of the thin films, we can see very coherent lattice, okay, demonstrating the high quality of these thin films. With these high quality thin films, we went on to measure the magnetic field response of these superconducting materials. Here, I'm showing you the superconducting transitions after a magnetic field were applied both along the perpendicular and parallel directions for all these samples. Okay. From these data, so qualitatively, you can already see that the system show a little bit of anisotropy because you see the suppression of superconducting transitions were not the same when you have magnetic field applied perpendicular and parallel into the sample plane. Okay, so there is a bit of anisotropy in the system. This is true across different compounds. If one visualizes what I just told you by plotting the so-called upper critical field, a field that can suppress superconductivity or even kill superconductivity, completely kill the superconductivity, for the magnetic fields applied along different directions, you can see that indeed there is a strong anisotropy. Okay, and this is marked by the analysis of vortex dynamics in the system from these measurements. However, what is surprising or interesting here is that so samarium, in terms of their ground state electronic structure, particular considering the 4f electrons, they should look more like a neodymium nickelate, which were reported already previously in the literature. Okay, but their upper critical field behavior is quite different. Okay, so here in this plot, I'm showing you a comparison between all these rare earth nickelate systems, where you can clearly see that for neodymium, the upper critical field along two different directions are below the Pauli limit. Okay, while for other systems, for lanthanum, praseodymium, samarium, including samarium, they all show behavior that are at low temperature are above the Pauli limit. Okay, and in terms of their temperature dependence, you can see that the samarium nickelate seems to more follow in the lanthanum nickelate. Okay, so this poses an interesting question, okay, about the dimensionality and whether the system is isotropic or anisotropic. It poses also an interesting question as I just mentioned, why, in terms of the ground state, the samarium system should be more like a neodymium, but it behaves as more like the other two systems. In order to get further information regarding this question, we also performed the upper critical field measurements in a rotated sample configuration. This is to say that we can rotate the sample within magnetic field and try to measure the magnetic field response as a function of the angle. Okay, and we have a well-established a formula to capture these behaviors, right? In terms of their dimensionality. Okay. To put everything in short, as you can see, the behavior can only be captured by considering both a 2D scenario as well as a 3D scenario. Of course, this is at a constant temperature, right? At a certain temperature, at a low temperature, well below the superconducting transition. And we performed the similar experiments across these different materials or samples. We found a similar behavior marked by their first anisotropic behavior, but at the same time, in terms of their angle dependence, there's a bit of isotropic or more 3D behavior at play as well. So in collaboration with one of the today's panelists, Professor Qi Wang from Chinese University of Hong Kong, we performed some X-ray scattering measurements on these samples. Okay, these X-ray scattering experiments provided some indirect and independent access to the dimensionality of the system. So particularly, this X-ray scattering measurements shows stronger hybridization between the rare earth 5D orbitals and the unequal 3D orbitals. Okay, so marked by these key feature on the resonance inelastic X-ray scattering measurements or data. So this is a piece of evidence to show that the system might be in a situation because the lattice strength, okay, the hybridization or crosstalk between the rare earth elements, which sits in between the nickel oxygen planes, are more dramatic or severe. Okay, so this is can be taken as an indirect evidence to probe the dimensionality of the system alongside with the transport measurements that I just showed. Okay, so to put everything to summarize what we found in these different materials in different samples, we plot the transition temperature as a function of the C lattice constant in our thin films and put them together with all the data reported in the literature. We found an interesting trend and very clear trend. It seems that the TC correlates very well with the C lattice constant, which again is in line with the strategy that I mentioned at the beginning of these scientific part. Okay, so this is a clear measure and clear sign for us if we want to further boost TC in this material system. Okay, so very close to the end due to the time limit. Let me just quickly flash our recent ongoing efforts. So we try to vary the concentration of the europium dopant and study very rich physics in the phase diagram. So okay, these are the raw data of the resistivity curve as well as superconducting phase diagram. This is still ongoing work. Okay, so we also try to characterize the valence state of the europium, the dopant into the system, and by doing X-ray absorption spectroscopy, we were able to show that indeed the europium changes valence as you dope into the system. Okay, so with this, let me try to make a summary here. So what I wanted to tell you is that the Nickelates have emerged as a new family of high-temperature superconductors. It's one of the newest materials platform for us to study high-temperature superconductors and hoping to fundamentally resolve the puzzle of a high temperature superconductivity. Okay, so I talked to you about our recent efforts in increasing TC in this system by introducing smaller ion elements such as samarium. Okay, and I also show you some current progress and trying to ask this question about the role of samarium and europium in the ground state of this inferior Nickelates system. Okay, so here are some research papers that we posted and published recently. And I would like to acknowledge my collaborators, of course, across different institutions who contributed to this work. And just as a very short advertisement, so at the City University of Hong Kong, our group focuses on bringing interfaces, oxide interfaces, or oxide heterostructures into the study of very fundamental problems or questions of condensed matter physics. We are hoping to find emergent state at the oxide heterostructures. And with that, and a very beautiful video about our department, let me stop here. I think I've already used my time. And thank you very much for your attention. I'll be happy to discuss with all different experts on these high temperature superconductivity problems. Thank you.